Hey everyone, my name is Agustín and today we have the lecture on backtracking. You'll have to forgive me, but there is a construction in progress on the building next door, so there might be some noise in the background. I have made some tests and I think there's not too much noise, but nevertheless there might be noise, so again, I'm sorry about that. So, backtracking. What is backtracking? I guess most of you probably have an idea, have probably coded at least one backtracking problem before. But I chose this topic anyway because I think as a region, compared to other strong regions like say China, for example, where Latin America is quite well, compared to China, relatively weak at backtracking, and I think Latin America is comparatively stronger at other topics, so backtracking might be a weak spot. That is my general impression, and it is not rare to find backtracking problems at the ICPC World Finals, so that's why I think it is a good idea to practice that. So then, what is backtracking? Well, there is a common misconception, sort of, that backtracking and brute force is more or less the same, but when you have a complicated recursion and you don't know the number of steps, and so you do it recursively and add some pruning, then that's backtracking. Well, it's not exactly like that, so let's get that clear. It is not a requirement that a backtracking code has to be recursive. That's not the important thing. What matters is that in brute force, you actually generate all the solutions and try them all. Now, what exactly does it mean to try them all? Well, that depends on the problem. Sometimes you have to check each solution and evaluate it and calculate its cost and compare it to the global accumulator with the best cost. Sometimes you have to make some checks to see if it is valid, and if it's not valid, then you discard it. Otherwise, you count it in the total count of solutions. But this is the basic principle. In brute force, you just generate all solutions and try them. Now, this works at the level of complete or whole solutions. That is why brute force algorithms are conceptually so simple. Just check all solutions. You never have to check a part of a solution, and that is the key difference with backtracking. In backtracking, you generate the solution step by step, so it's automatically more complicated, more complex, because you are, after all, generating the solutions. So you can use the backtracking and say and think like, okay, it is like an advanced way of brute force. Instead of generating all solutions, and I don't care how, in backtracking we care that we make it step by step, and it is important. Why is it important to go step by step? Because you have to try the solution at each step. That is very important. And again, what does it mean to try the solution? It depends on the problem, but that might be checking that what you have already constructed is still valid. So we have to check even before having a full solution, and like brute force, where you have a function that takes a checker that takes a complete full solution and runs the checks. In backtracking, each time you do a step, you have to check, okay, now given the steps that I have already taken, is it okay? Is it wrong? And also, what is the cost of the parts that I have already done? That is very common. You go calculating the cost step by step if you can. That is the true difference. And I like to sum it up by saying that brute force is for, if. While backtracking, on the other hand, is for if. Now, that this might look like a joke, but it's not. This is actually the difference, and this is actually an example of why a backtracking algorithm might actually be just a simple for loop. The key part is that for each step that you make towards the solution, you start checking and making validations. Now, when do you use brute force and when do you use backtracking in a problem? Well, basically the heuristic is that you use brute force whenever you can, because it's simpler. It's the easiest method, typically. You just generate all solutions, no matter how. If you end up generating them similar to backtracking or not, you don't care. You generate them somehow using next permutation, function, whatever, and then you check. That is typically easier and the easiest way. But as we will see, backtracking almost always backtracking algorithms almost always have better complexity, even in terms of asymptotic complexity, not only better constants. And those, when you don't care about how easy it is to code it, well, backtracking is the better choice. So let's do an actual example. Let's say I call f of n to the number of positive integers of exactly n digits, such that every prefix of the number is a prime number. Exempli gratia, this number is a valid number according to my criteria, because 7 is prime, 73 is prime, 339 is prime, and the full number is prime. So this one would count towards calculating f of 4. F of 4 would be the number of 4-digit integers satisfying this property. Now, this would be a brute force algorithm to calculate f4. We can initialize a counting variable to 0, and then we just generate all the possible values of each digit, A, B, C, and D, check whether all the required numbers are prime, and if all of them are, we add to the total. We could easily calculate if a number is prime for the purposes of this problem by first pre-computing the primes. And also here I am writing so that it is easier things like ABC, which means ABC taken as a number, but you of course can compute it as 100 times A, 10 times B, and C all added together. But this is the main idea. So when you have to compute f of 4, we see that we have 4 for loops iterating temp values each, and then all the checks. So the complexity of this solution would be 10 to the power of d for the code solving a digit problem, that calculating f of d. Probably even more, because for each of those possibilities in the 4, we have to make all of these checks, and the number of checks that we will have to be grows as the number of digits. But 10 to the power of d is the main huge part. So to compute f of 4 would take like 4,000 steps. Clearly that is too much. What if we generate the number digit by digit? Well, we already are generating it digit by digit, but what if we check digit by digit? Well, that will give us a backtracking algorithm. So the backtracking version, we would rearrange these blocks. Now this would be the backtracking version. Remember that for a backtracking algorithm, we have to generate step by step, and we have to try everything, the solution at each step. And that is what we can do here. First, we choose the first digit A, and we can already check something, because if the first digit is not prime, we have already failed. So we put the first if. And so on. Once we have chosen the first two digits, we can check that that part is prime before continuing. And so on. So this is what I mean by brute force is for, if, while backtracking is for, if. When you implement backtracking recursively, because you don't know the exact number of steps, and those you can not create this very simple for if method. Nevertheless, it's the same idea, because you put your if checks inside the recursive function. So you might count each calling of the recursive function as each of the fors where you call a branch into many different calls. So the ifs and the branching will alternate. So you are checking at every step, and that is the important part. But it is not a requirement for backtracking to actually have a recursive structure. That is just the most common way to implement this for if thing when you don't actually know the number of fors beforehand. Now, what is the complexity of this other method? Well, something very common in backtracking problems is that computing the exact time complexity or being sure of the time complexity is hard. But almost always the complexity is much better than brute force. Here, for example, we might very easily see that the possible values for A, B, C, and D, when you want to actually pass the following check, are only 2, 3, 7, and 9. Because otherwise the number won't be prime and it will fail the check. Except possibly for the first digit that might be a 5. So the complexity must be at most something like 5 for the first A times 4 to the power of D minus 1. And also we can even get rid of this extra times D factor. Because we don't have all of the checking to do at the last step. We have been doing the check in the middle while creating each step. So at the final leave nodes of the iteration, very little checking is left to be done. But even if this is not correctly implemented and you have an extra times D factor, we see that already compared to the previous 10 to the power of D complexity, this is already much better. And still, that is a huge overstating of the complexity. A much better bound for the true complexity can be obtained by noting that by making all these checks in the middle, we are only going through valid solutions for the previous digits. Once we've crossed this first if, we are sure that the first digit by itself is prime. But once we've crossed this second if, we are sure that both A, B, and A are prime. And thus, this can only happen at most F2 times, because the whole number AB has to be one of the valid numbers for 2 digits. And similarly, we will only pass this if f of 3 times. And then for each of these, we will have to iterate 10 times. So a much better bound is that the complexity will be 10 because of this final 4 times f1 plus f2 plus f of d minus 1. So in our example, instead of going through all the 1000 numbers, we would only have to go through f1 plus f2 plus f3 numbers. So like we only have to go through the valid previous numbers. And the thing is that this grows much slower. We can experimentally check some of these values and we can see that the f numbers are growing very slowly. So the fact that we only have to go through the previous solutions, which are very few, makes this method very fast. And this is a very common pattern in backtracking algorithms. When you can create it step by step and you make all the checks in each step, when there are few solutions in total, the backtracking process will be very fast because it will be proportional to the number of solutions, and indeed the number of solutions is small. And thus, even though we are not making any advanced pruning, any interesting check, we just changed the order of the if. Like I said before, backtracking almost always leads to much better asymptotic complexity than brute force. Even though sometimes it is hard to calculate it, we were able to make an interesting complexity analysis in this case and understand why it will decrease so much. But even if you don't understand it, it almost always will lead to massive true complexity gains. At the very least, by doing all the checks and calculations in the middle, you will get rid of an extra n factor at the end, because of not having to do all the ifs and all the calculations together at the end. For example, suppose you have a problem where you have to check all permutations and try them all to get the best one. And then for each permutation, you have to go through the adjacent numbers and make a very complicated calculation about those numbers. Like, I don't know, f of 2, 3, and f is a black box, a very mysterious, very chaotic function. Plus f of 3, 1, plus f of 1, 4, plus f 4, 5 would be the cost for this precise permutation. So if we use a next permutation function, do while next permutation and check all of the permutations, and then inside the while loop compute the cost of each permutation separately, then our complexity will be n factorial to try all permutations times n, which is basically the same as s plus 1 factorial asymptotically, because in the main check will involve a for, where we have to go through all of these adjacent numbers, making a call to the function f and adding dot all. Now, if instead we were making this step by step in a backtracking fashion, adding each number in turn, if we implement it correctly, then we can have a global variable where we're computing the current addition of costs, and so each time we add a new number, we can add that factor immediately to the running total. Then when we get to the end of the backtracking process, we don't have to perform an additional for loop, and thus the final complexity will just be n factorial without this extra pesky n factor. So typically, at the very least, if there is no pruning and nothing good going on, at the very least the backtracking method will get rid of this n factor. Well, not always, but it is very, very, very common. Another example of what I mean is at this same example, even though we have only one if here, if we implement this without being careful, the complexity will be the number of times that we reach here. Let's call that t, the number of times we reach this if checking. So the complexity will be t times the cost of the if, and here we will have to compute the number, let's say 1000a plus 100b plus 10c plus d. So in general, this is proportional to the number of digits. Let's call it n. Here n is 4. So the solution would be t times n. But we can easily get rid of this extra n factor, taking advantage of the fact that we are doing backtracking, and thus making sure that this cost is not paid all at the end, but that we can spread this calculation, because this cost would have to do with having to compute this whole number. But we don't want to compute it from 0, because we would also have to compute it here for the first 3, here for the first 2, etc. So AB can be written as 10 times A plus B. Better, let's say that the number AB, understood as a number, equals 10A plus B. But the number ABC equals 10 times AB, the previous one, times B, and so on. And this is just a one operation or constant time. So by doing it this way at each step, we can spread the cost of this number building across all of the 4s, and thus the final complexity would be just t. This is a very common pattern, a very common idea. Just to make clear with a drawing what is happening, we can see any backtracking problem as involving a tree, which actually represents the solution building process. In the tree, each level of distance from the root will represent one step of of the solution building problems. Remember that every backtracking involves creating the solution step by step. So the first level will have all the partial solutions after one step. The second level we have the partial solutions after 2 steps, and so on. That is why the root is the initial empty sort of. We have not taken any steps, we have not started yet, and that's the initial situation. So in our example code with force, each time that we successfully pass one of these if checks, then we are going to a child node of the current situation. So each of these edges in this generic tree representation of the backtracking running, of the backtracking execution, corresponds to one of those checks being passed. Those that are failed are typically not thought of in the drawing, but would be like failed children, so to speak. The for will iterate the 10 digits and will generate some attempt that will fail and not call recursively when we implement it recursively, or will not keep going on when we implement it like this with if. But that can all be considered part of the cost of this node. Each node has a cost which corresponds to testing and trying and generating all the steps required to go on. And those solutions that reach the final level after all the solution creation steps are the candidate solutions that we test. In this problem, we just want to count them all because we have already made all the tests in the process, which is very common. And those, when we get to the end, we just add to the solution. Now, in these terms, what I mean is that very often, instead of making an expensive linear time check at each of the leaf nodes, which corresponds to the complete solutions, we can compute this partial cost at each node, so that each node knows its partial cost up to the moment, and thus the computation to go from one partial cost to the next will typically be constant time. That way, when we reach a node, we already know the full cost, and we don't have to make this linear time computation. Effectively, it's like changing from paying linear time only at the leaves to paying a bit more but constant in all of the nodes. But this is typically a better complexity. It is better to spread the cost. Now, I want to mention two principles which are very common and used all the time. The first one can be summarized as generate, not filter. What does it mean to generate, not to filter? Well, let's say I want to go through all the even numbers from 1 to 1000. Well, to filter means saying, okay, let's go through all the numbers from 1 to 1000, and now let's filter the ones I'm interested in. If the number is even, then I can do whatever I want to do. But this is inefficient. It is much better to somehow generate precisely those that I am interested in. In this toy example, this is very easy. Instead of going through all numbers and checking the parity, I can skip and go only through the even numbers by jumping in increments of 2. I will increment I by 2 on each step. And that will directly go from 2 to 4 to 6 to 8. So it will be twice as fast. I will not have to go through all the odd numbers just to check and discard them. In this sense, this general principle encourages us to never look at wrong solutions. It avoids going to some solutions that are not important. Of course, sometimes it is actually hard to generate the solutions because there is no obvious pattern of how to find them or how to create them orderly, and thus just filtering the only thing that we can do. But whenever there is an option to generate them, it is better, and it is good to explicitly have this principle in mind and try to think, okay, how could we generate these numbers instead of filtering them and checking? Is there some way that we can directly generate them? Do they have some structure? Well, that's very common. For example, this principle applied to the previous problem, instead of trying all of the 10 possible values for the digit and for each of them checking if it is prime, we can check the structures of the primes and notice that all prime numbers except for 5 end with either 1, 3, 7 or 9. So those are the only possible options for the digits, because we are currently generating all 10 and filtering those that create a prime number. But now we know that because of how the prime numbers are, there are only 4 candidates. The other ones would be filtered anyway immediately. And those we can generate these candidates instead of filtering to arrive at them. So we could change these 4 candidate values, except for the first digit, of course, which might be 5. Now we have a second example. Now we have a second principle which says to generate numbers in a single way. Well, I say numbers or solutions, it depends on the problem. Generate numbers or solutions, generate solutions in a single way instead of many. This, of course, might be difficult in some problems and easy in others, but it is worthwhile to think about this consciously and try to avoid generate a process of solution creation that can arrive at the same solution by taking different paths. This never happened in the previous example that we had because we tried the 10 values for the first digit, the 10 values for the second digit, and so on. And so there were no 2 ways of choosing that created essentially the same solution in the end. So we didn't have this problem, but sometimes it can happen and it is much better to avoid it, both to make the code simpler because we don't have to remove duplicates, increase the runtime. And this comes to mind regarding one problem in the last maratona or tap that we had, where there was a problem where essentially which essentially had to do with Fibonacci numbers. So for that problem, you could first generate the Fibonacci numbers. And the question was, given, essentially you had to compute, given a very large number, maybe like 10 to the power of 15 or something like that, I don't remember, but a large number, we can't test in a very naive way. Check if a certain number can be written as a product of Fibonacci numbers. So for example, 30, it is possible because you can write 2 times 3 times 5, which are all Fibonacci numbers. But for example, 14 is impossible because there's no way that multiplying Fibonacci numbers creates number 14. In these problems, there were many submissions in the real contest that were getting time limit exceeded and were almost right, but they were failing to apply this second principle. They were generating the solution in many ways. Let me show you. The code was something like, it was essentially a backtracking implemented by a recursive function, f, which made the check, so it returns, say, a Boolean value to say if a number can be written or not. And to check, basically, it tried all the Fibonacci numbers, which were pre-computed in a list. They were not too many because the Fibonacci numbers grow exponentially. And for each of them, we check if we can divide. If n mod x equals 0, then we can divide it. And so if we can write the divided number also as a product of Fibonacci numbers, then we return true. If we fail to do this, we return false. This is actually lacking a base case, which can be fixed by adding an if here. If n equals 1, then we return true. We would consider 1 to be a product of an empty number of Fibonacci factors. So this is correct, but the problem is that this is way too slow. This is exponential in the number of Fibonacci factors. And I'm pretty sure that 7 times 10 to the power of n for large n is a case that makes this solution explode. It makes it too slow. Actually, I did the test cases for this problem, and I remember adding this test case or a very similar one. It had there were various test cases very similar to this idea, that basically kill the complexity of this kind of backtracking solutions. Because this one cannot be written as a product of Fibonacci's, this one is impossible. I don't remember, maybe this one is possible, but a slight modification that has this troublesome 7 factor, maybe instead of 7 you should use 41, another prime that never appears. I don't remember, but something like this, a complicated prime that never appears times this simple factor. And the thing is that since 2 and 5 are both Fibonacci numbers, there are lots of ways to divide the number, this 10 to the n number, which is essentially 2 to the n times 5 to the n. There are a lot of ways to divide by 2 and 5 in many different orders to get to the same numbers to check. Let me show you. For example, if you divide by 2, then by 5, then by 2, then by 5, you get to the original number divided by 100. But if you divide first by 5, then by 2, then by 2, then by 5, you also get to the same number to check. And so on. There are lots and lots of ways to make valid divisions that will lead you to different numbers to check. So there are lots of different paths in the solution creation step by step. This could be considered a backtracking algorithm, by the way, because we are explicitly, well, it's not explicit here, but we are step by step constructing this product of Fibonacci's, and on each step we choose x, one factor of the product, and then when we say okay, this could be a factor because it divides the total, we will try to see what all the other factors should be, but that generates the same list of factors in different orders many times, and this is exponential in the number of factors, and so this will be too slow. There is a way to solve this for this particular problem, which is maybe not the best way in general, but many times it will help, and it's basically to turn this into a dynamic programming solution. Basically, we are arriving at the same problem from many different paths, and whenever that happens, it might be in a backtracking-like recursion or in any recursion. Whenever that happens, we can use memoization to avoid having to compute the same thing over and over again. Thus, adding memoization to check if we have already solved a problem is enough to make this work fast enough for that problem. But another solution is to apply the principle that we've stated, to generate things in a single way instead of many ways. How can we change our solution creation process, in this case, to make it such that each possible solution, which here would mean each set of factors, is tried only once and not many times? Well, the problem here is that we are trying the same factors in different orders, so we should fix the order. We should actually fix the order. So in our product, we would like to generate all the different factors, for example, from smallest to largest, or you can do it from largest to smallest, it's the same. So when we call and ask for the product to make up for the rest of the number, we would like to ask that all of the factors are at least x if we're going in order, because if then we try a smaller number, we will not be trying the numbers in order, and we want to try them in order simply to avoid generating the same set multiple times. So we will need two parameters, one n and s, let's call it from start, which says the minimum value possible. And those, when we try in all fibos, we will only consider those that are larger than s. So the simplest way would be to add here an if x is at least s. But if the list of fibos is ordered, we can apply the first principle, generate, not filter, and instead of running through all of them and adding an if to check if they are greater than s, we can actually do better and check at what index in this list we have to start, and start right from there, never looking at the previous one. that will be better and can be very easily implemented if these X and S are indices into the list of Fibonacci's instead of just values. So yeah, this was a very, very common problem why a lot of teams, and I mean a lot, I probably saw like 6 teams myself during the contest having this precisely this time limit, which would be solved by adding this parameter and creating in order, or by using dynamic programming. So there were probably more. So yeah, these are simple principles, but important ones. Now, at least in competitive programming, some of the problems where I have seen that it is more necessary to get up to the last bit of performance and have a very optimized code is in backtracking problems. I mean, it's not uncommon that a backtracking solution at which is on the right track is implemented in a backtracking, but in a very slow way, and thus it fails. So here are some tips to get maximum performance, especially in backtracking algorithms, and which might not be so obvious if you've not coded many backtracking methods before. Anyway, I should first say that improving the algorithm by making smarter, better, more effective prunings, for example, is usually better, or avoiding repeating solutions in a smart way, or generating or using a more efficient generating process that goes directly to the right solutions. Those kind of changes that fundamentally change the algorithm usually have even more impact. But when you already have decided, well, these are the things I want to check, this is the backtracking idea that I will use, well, you can change how you implement it and get a lot of performance difference. One very simple and quite often overlooked method is by using bit sets or bit masks. Since backtracking problems usually have quite a small bound, you will often be using bit mask. For example, if you have a graph and you are running a backtracking problem, you will often need to go to the neighbors and do something and check something and maybe change, kill all the neighbors of a certain node, etc. Many times you can completely avoid looping and doing a for about that by using a lot of bit masks. Like, instead of having an adjacency list, you can have an adjacency bit mask, so to speak, for each, so that you have a G of I, and instead of this being a list of all the neighbors, no, this could be just a bit mask which has one precisely at the neighbors of this vertex. And those you can, for example, I don't know, remove from the set of allowed vertices all the neighbors by just using some bit operations, and so on. Almost lots and lots and lots of backtracking problems, not only those about graphs, can be improved by using bit masks instead of lists. It's quite easy to overlook that. So I encourage you to learn a lot of bit tricks. And about speaking of bit tricks, this is useful for other problems as well, but you probably should know at least how to iterate only the ones or zeros. Like, if you have a mask that you know that has only 3 ones, for example, and you want to quickly go to those 3 ones and know their indices and not have to check all of the bits one by one, you have to know how to do that. And basically for that, it's very useful to know how to count leading zeros and how to count trailing zeros. These details depend on which programming language you're using, but you will find tutorials probably in Codeforces and in Topcoder and many other sites about bit operation and bit tricks, and you will find many. Similarly, you will not want to have dynamic memory allocations going on, because those are much more expensive than normal operation. This includes, for example, vector creation. So it is generally fine to you can always use array probably, and you will do that for many backtracking problems when you go for maximum efficiency. But usually using vector is fine as long as you never create a vector. So basically, all your vectors should be global variables, such that you create them only once. You only have to pay for the memory allocation, and that's it. You don't want to be allocating memory dynamically during the main backtracking function, because that's much slower than just normal operations. Similarly, very slow dynamic memory structures like map or set are a last resort if you're doing backtracking, because they are much slower. Another very common trick is to modify a global state instead of making copies. So for example, when we have a general scheme of what a backtracking is, whenever you have already built a partial solution, say you're in a graph problem and you have to choose some nodes, you have already chosen some of them, or maybe you are building a subset of allowed numbers, and that involves already creating some structures. Well, for each of the possible options, your current solution under creation will change. Maybe you have to add nodes or remove nodes that are no longer valid or something like that. And you want to be able to undo those changes when you go back. So the easiest way is to just copy the full structure with the change for the subproblem. So that way, undoing that work for the next problem is for free, because you just stop using the copy and go back to the original one. But many times, instead of doing that, you can have a single global state with the current situation of the graph or the solution. You might be adding edges, removing edges as you build the solution. And then you modify a global state. So the pattern for this in the code is typically like, well, maybe there is an if I have to call a subproblem because I will try to make a modification. They change, or let's say do change to the global state. Then you will call the solution to the subproblem, which will operate on the global state, which has already been changed. And then you will have to check other solutions and avoid leaving the global state destroyed. So then after calling, you will undo the change. This is a very, very normal pattern. And about this, what I recommend is when you have a global state of the backtracking, which is very common to avoid having to copy a lot, create one struct state having all the information that you want. And this is very good because once you might say, oh, the state is very small, I won't do it, but do, because it encourages you to code better, and with that will reduce bugs, which are very common, very, very common if you have to do something like this, and they are very common in backtrackings in general. For example, as soon as you do this, you can add methods to this state that implement a higher abstraction of things. For example, the state might have spent money and acquired money, because you have to remember those two numbers, how much you win and how much you lose. But it is very useful to have a method div or net or something that already does the subtraction. One such logical candidate for a method are the change methods. They will possibly take parameters indicating what or how do we want to change it. For example, this might be a board where we are, the state might be a two-dimensional board where we are adding special cells. We have to put some, I don't know, light bulbs illuminating everything at some special squares, and the change might be, okay, add a lamp at a certain place. And probably there will be an undo change, which is similar. Well, these are obvious candidates because that way in your main code you might want to call this change and unchange many times, and so it is very good to have it on a method. And also another advantage of the struct is that you can before coding this change and undo change method, before everything, you can take advantage of the fact that you have encapsulated the whole state, and now implement this as just making a copy like this. You can make a copy and save the whole global state, call the function, and then restore it. I recommend that you always do it like this and test the code so that you are quite confident that it is correct. And then, depending on the situation, you might submit it first and see if it works, and if it gets time limit exceeded, then okay, you can work on improving this so that you don't have to make a lot of copies and use more memory every time. So you can just make the little change and undo the little change, but you will have some confidence that everything is correct, and you just have to implement these two methods. This is especially true when you can't calculate the complexity of your backtracking, but you feel because of experience that it should probably be enough, and you don't probably need to squeeze up to the last microsecond of performance. Then okay, maybe you decide I will send this because I will submit this to the judge because I think it might be okay. And finally, my last performance tip is to pre-compute everything, and I mean everything. In backtracking problems, it is very common that you will be using it is very common that the whole backtracking runs in exponential time. As we've seen before, that is not always the case. You could have backtracking problems running in polynomial time because they have a few steps with not too much branching, and so it is like 4, and maybe it's quadratic, and that's okay. But most often than not, backtracking problems involve an exponential runtime, and so you will be running the same critical part of the code, the backtracking main step, a huge number of times. So you want that part to be as efficient as possible. So many times you might be asking questions or calculating things of which there are only a polynomially many possibilities. Whenever that is the case, just pre-compute them so that you don't have to do the calculation every time, so that you can just read the result in constant time, and so you can make the main step extremely efficient. This goes for maybe quite obvious things, like for example, instead of computing a path in a graph every time, just run Floyd Warshall first and have all the paths pre-computed. But maybe, I don't know, you have a node and you have to check its neighbors to see if there is a triangle, or check, or you want to know, given 3 particular vertices of a graph, if there is a triangle, but which you will be asking for depends on each step of the backtracking in a very precise way. Well, it doesn't matter, just pre-compute a table, a cubic table telling you, I don't know, triangle of ABC, whether that is a triangle or not, so that the backtracking, when it needs, can ask this table in constant time. Because maybe you will be asking that table tens of millions of times, but pre-computing the whole table is not significantly more expensive than the main backtracking, so it's better to do it so that the other part runs much faster, and like that for everything. You might be doing some very small simple loops for counting some things on at the moment, but if there are a few possibilities, just pre-compute them. Everything will be faster. So try to make everything a constant time during the main loop. Now, this emphasis about performance will most often be necessary whenever you as a contestant are not sure whether your backtracking solution should be enough or not. And that is perfectly valid and will happen and can happen because a lot of things. it can happen because basically there is not much time left in the contest, and you think that your best shot at solving a problem is coding a backtracking as best and as efficient as you can and sending it and hope for the best. It might be the problem setter's intention or not, but if that is what you think gets you the best chance of solving the problem, then okay, maybe that's your last resort. But it might also be the case because the problem is set in such a way that basically your only reasonable approach is to make an efficient backtracking and hope that your pruning and your efficiency is enough to solve the actual test cases. That might happen in a contest, and you should be prepared because it's not like as if the test cases themselves were actually wrong. I mean, they might be weak, and there are a lot of weak test cases out there. So it might be a thing. You should never expect to have wrong test cases. That is, test cases having a wrong solution, because that is very, very rare. But somewhat weak test cases or problems where you can have a solution that passes with an efficient backtracking, that is not so rare. I am not encouraging you to always go for it. That is a very bad idea, but sometimes that might be the best. Now, this is getting slightly philosophical, but about problem setters, many, and this is the point of view, if I don't misremember, Piotr had expressed this, or maybe it was not Piotr, but some other legendary ethical forces, I am not sure. But definitely some legendary ethical forces expressed that there are bad backtracking problems and good backtracking problems. And basically, there were like two cases of good backtracking problems from a problem setter perspective. And this is quite subjective, but you will find out there, and they were very common, like 20 years ago, they were probably very, very common, what can be called bad backtracking problems. And bad backtracking problems are those where basically the expected solution is, well, guess what optimizations are enough to pass our secret specific test cases? Like, basically I want the contestant to code this or that optimization. That is my plan, so to say. So I will code a backtracking with this or that optimization. I will think of some test cases as best as I can, and just empirically test it and set the runtime such that that solution passes. And then I hope that the contestant thinks about those optimizations or some other that are at least as good. This is typically bad problem setting because there might be other test cases where those optimizations are very bad unless you have some put some extreme effort into the test cases. And the contestant might think of another optimization that is very good for those other test cases, but not for the ones that are the official test cases of the problem. And many feel that is unfair, basically. So that leads us to what are good backtracking problems. Well, according to this clearly subjective criteria, one of two things should hold. You either can prove reasonably well that for any possible input, and that basically implies that it's possible to give a good enough complexity analysis, or two, you can locally test it on every input to see for yourself whether it is fast enough or not. This will very often mean that there are actually very few inputs, which also opens the door to actually hard coding the output solutions. Basically, in both of these cases, you have a reasonably good way to be sure that your solution will not result in time limit exceeded before you submit it. You don't have to resort to make speculative submissions. You always can, but you're not required to do such submissions to solve the problem. We will see two examples of the first kind of problem and one example of the second one, which appeared in the last Latin America regional contest. For our first example, we will solve the max independent set problem. I should mention that with the same ideas you can solve the maximum clicker problem and the minimum vertex cover problem. You can look it up. They are basically equivalent to the maximum independent set problem. You either have to complement the solution set or you have to take the complement graph, but they are basically the same. So the max independent set is a very well-known graph problem where you have a graph and the aim is to find a set of nodes that such that there are no two nodes which are neighbors in the set. For example, I can take these two nodes and this is valid because there are no two neighbors in the set. And in this case, this is the maximum independent set. It can be proved that it is impossible to put 3 nodes in this graph such that there are no two neighbors. So that is the problem we want to solve. And we will solve it by backtracking. First, just as a means of comparison, we could compute what would be the complexity of a brute force solution. What would be a brute force solution for this problem? Basically, we can use some bit masks to iterate over all possible sets. There are 2 to the power of n different sets with n vertices. And we could try them all. And for each vertex, we would probably need to check every possible edge in the graph. Let's say the graph is a general graph given with an adjacency matrix. So then we will have to check about n square edges. So this is the final runtime, order 2 to the power of n times n squared. That's pretty terrible, but it might be enough. Like, I don't know, if for example, we have an instance of this problem where n is at most 15, then we're probably okay with the brute force. It depends on the time limits. And then, unless they are much less than a second or something like that, that should probably be fine. But we want to do better. We want to do better than this brute force method. So we want to use backtracking, of course. Now, for backtracking, we know that we have to think in terms of steps. So we have to think, how are we going to build the solution step by step. Now, a very natural step for our step-by-step algorithm is to pick a node, one specific node. We could take an arbitrary node and choose what to do with it. So there are only 2 options per step. At each step, we have to choose a node, and there are 2 options in principle. We can choose to ignore it because we will not use it in the final independent set, and that means that we can basically ignore it and delete it from the graph. And the other option is that we can decide to put it into the independent set. This is the situation. We have a graph, and say, for example, that we are considering this vertex in the middle. So we have 2 options. We can choose either to use it for the independent set or not to use it. If we choose not to use it, then we can delete it because the independent set that we will choose will be chosen from the other vertices, and those it will be an independent set of the graph once this node is removed. So this is one option, and here we will have to solve it, and the solution will be the solution to our problem. In the other case, if we choose to use this problem, this vertex, then we would like to call the remaining problem, but what we can see is that the neighbors of this chosen vertex cannot ever be used again at all. So they should be deleted from the graph. We can delete them because it's also an appropriate way to encode the fact that we have chosen this vertex and cannot choose any of its neighbors. Otherwise, we would be creating an invalid solution. So we will delete the vertex and also all of its neighbors, unlike this case where we only deleted the vertex. Now we will delete the vertex and all of its. So in this case, when we choose the vertex, this will be the remaining graph where we can find an independent set. Of course, in this case, the partial solution will have to remember that it has already placed one vertex into the set. If we only care about how large is an independent set, but not which nodes make the maximum independent set, we don't need to remember which it is. We can only keep a number of nodes already in the set, but otherwise the partial solution would look like this. It would say, okay, this vertex has been chosen and these are the vertices that can still be chosen. The important thing is that for all purposes, this vertex is the same as if it was not there. It's just for the purpose of counting and knowing which is the solution, but the problem that we have to solve now is the remaining graph after deleting that vertex and its neighbors. So that is a basic setting of our backtracking. We will consider this backtracking solution, but improved with several interesting prunings. We will see it. Okay, how do we implement it? Well, we can implement it very efficiently with using bit masks. Using a few carefully selected bit masks, like I said before. For example, the adjacency lists could be represented directly by bit masks. The set of vertices that still have to be considered and are still an option because are not neighboring any of the chosen independent set vertices. Those that I am painting in white here can be kept in a bit set. Using the tricks of selecting the next bit quickly and bit operations, we can basically make all the operations in our step in constant time. So the only time that our solution will spend will be branching and creating new search nodes. But each step will be constant time. And that is very good because we have already improved to time 2 to the power of n, just by using an efficient backtracking implementation with bitmask. Even if the implementation was not efficient, it will probably just do order n things per step, so it will still be an improvement over brute force. But still, using bitmask, we can completely remove this 2n² term. This is because the branching factor in this problem is basically 2. For each, we have n steps at most, because after n steps there will be no more nodes, and each step we have only 2 options, either keep the node or remove it. Now, can this be improved? Well, it can. An interesting heuristic to note is that, when you choose a vertex, you will destroy it and create 2 new subproblems, basically. So you can think of this as an operation. This is very common in backtracking. You have the original problem. Here, let me draw it again. This was the original instance that we wanted to solve, but it might have been an intermediate instance that we were solving. And for the purposes of backtracking, it decomposes into 2 other problems that we want to solve. So now, in order to solve this one, we are going to solve these other 2. Now, remember how we created these other 2 problems. In one of them, the number of vertices is reduced by exactly 1. So that one is easy, always 1 less vertex. But in case of the other problem, how many vertices we remove is not constant, but it depends on the degree of the node. Now, if we assume that we want our problems to have as few nodes as possible, which is a very reasonable heuristic. I mean, without knowing anything else about the graph, which would require more intelligent techniques and prunings. If we want a very basic estimate, we will think, okay, larger graphs are harder. So we would like to create graphs as small as possible. So as a result, a very reasonable heuristic would be saying, okay, let's grab at each step, let's grab the vertex with highest degree. We want to have the highest degree vertex, and that is the one that we will be using. That is a reasonable heuristic. We don't need it. In fact, for all the complexity analysis, I will assume that we don't. I will not need to do that. And maybe, and it might be the case, depending on the implementation, that actually going to taking the effort of using the highest degree vertex makes the implementation slower, because maybe we change from 2 to the power of n, worst case, to 2 to the power of n times n, if we happen to end up needing a factor of n in order to be able to get to the highest degree node quickly. That would be experimental. But anyway, it is an interesting idea that high degree is good. That is all that we will need for this purpose. Maybe taking the highest one seems like a very good idea, but maybe finding it is more expensive than what we gain. We don't know, but it seems like a good idea. So we will assume that we won't do it because it will be easier and will give good complexity guarantees actually. But the main idea remains that high degree vertices are easy, so to speak. So if we have a graph with a lot of degree, that is good, which is pretty logical. If we have, for example, to take it to an extreme, if we have a complete graph, everybody connects to everybody, then the algorithm would end in just n steps. Because if we use a vertex, then that prohibits using any other vertex. And so the backtracking tree would look like this. Okay, the option of taking the vertex, and that's it. There is no other option. If we remove it, then what do we do with the next one? We can take it, but there is no more option then, and so on. So it's there is no branching in this tree practically. So that's great. So hard instances end up being those where vertices have very few degree. So the other extreme would be n vertices with 0 edges. Well, that test cases would be the worst for our current backtracking implementation. That would kill our current backtracking implementation because in both cases, whether it takes a vertex or not, it will always reduce the number of vertices by 1. But it will call 2 new subproblems. So each additional vertex multiplies by 2 the time that we need to solve an instance. So it will actually achieve this 2 to the power of n time bound. Basically, it will end up looking at all possible subsets because they are all valid. But intuitively, when we think about this very extreme example, we see that it should be easy. So large degrees seem to be easy. And that is quite natural because of the way our algorithm works. But our algorithm is being slow for very low degrees. But intuitively, we should be able to solve those. Those don't seem, I mean, this seems like a trivial, very easy instance. There are no edges, so you can grab all the vertices. That's all. That's it. That's obviously the maximum independent set. So let's add a very simple condition to our algorithm. It takes an arbitrary vertex, but it checks whether the vertex has a degree 0. That's all, I promise you. This is all the change. The only change that we will do. I want you to think about an algorithm where we do just as I described previously, but we add an if, a check, a pruning, that if the current vertex, which is arbitrary, we don't check the whole graph to check if there is a 0 degree vertex. No, we just grab the next one, but we check its degree. If it happens by chance to be a 0 degree vertex, then, well, it is an isolated vertex. It has no neighbors. So it obviously has to be part of the maximum independent set. If we don't choose it, well, we could add it and it will generate no conflict. So it has absolutely no sense to check the option of not choosing it. That will obviously not be optimal. So that's it. We will add a check if this vertex has degree 0. Note that an important note, I don't mean degree 0 in the original graph. I mean degree 0 in the current step. So for example, the original graph here has no vertex of degree 0. Okay, let's say we remove this one. We could have removed any other, but let's say we happen to remove this one. We get to these two problems, and on the left one, whichever vertex we choose will have degree 0 now, even though originally it did not. So we have to be able, when we remove vertices, we have to somehow be able to update the degree of its neighbors, or at the very least be able to detect if the vertex has degree 0, because possibly calculating the precise degree will probably be hard, but we don't need that. We only need to check if it has degree 0, so that will probably be able to be done in constant time per step with bit masks. In fact, now that I think about it, we probably can actually keep the full degree by using bit masks, because we can take the AND of the current alive vertices with the vertex original neighbors masks and the number of ones in that mask, which can be counted with a pop count, which is a constant time operation ideally. That will give us the degree, so we could get the degree if we want, but we just want to check if that mask is 0 or not, so it seems easier. Anyway, if that vertex is currently isolated, we pick it. We don't check the option of not using it. Otherwise, we check both options. That's it. That's the only change. Now, you might be watching this and saying, well, that only that change cannot possibly reduce the runtime complexity. That must still be 2 to the power of n, right? That is too simple. It would be reasonable to think that, but unfortunately, it would be wrong. Amazingly, this change, this very simple check, makes a major impact on the runtime of the algorithm in the worst case. Obviously, this is no longer a worst case. This is an excellent case. The algorithm will just at each step take a 0 degree vertex and say, oh, okay, I have to pick it, use it, and that's it. So how, I don't know how a worst case will look. Well, I think I know, but let's ignore it from now. How can we prove that we have a better runtime? Well, let's check how we would have calculated the runtime for the original one. We want to compute f of n, the runtime of the algorithm for the worst case runtime for n vertices. Well, for the original, the recursion is very simple. For a problem with n vertices, you remove one and call 2 other instances. Now, how many vertices do those have? In case you don't grab the vertex, which is this example over here, you always have one less vertex. If you do, you have one less vertex because you don't have the vertex still, but you also have to subtract all its neighbors. So you have to subtract one vertex and you also have to subtract the degree of the vertex. Now, if we have no checks at all, the degree might be 0. So in the worst case, we would have fs plus 1, we choose not to use the vertex, plus fn minus 1, because actually this is 1n minus 1 minus degree, but the degree is 0 in the worst case. So that amounts to 2 times f of n minus 1. And this recursion obviously leads to a 2 to the power of n solution. Now we have the same idea, but now a vertex of degree 0 is a great test case. Basically, we remove this and just go to f of n minus 1. The function f is obviously increasing, so that is not the worst case. The worst case must not be a vertex of degree 0. And so by a very similar argument, the worst case must involve a vertex of degree 1, such that when we remove it and remove its neighbors, we're removing 2 nodes in total, the vertex and its only neighbor. So this is the new recursion that we get. And you might know this recursion because this is very well known, and this recursion is the Fibonacci recursion. So we get the Fibonacci numbers, and Fibonacci numbers grows as phi to the power of n, that is 1 plus square root of 5 over 2 to the power of n. This is a well-known property, which is approximately 1.62, I think, to the power of n. And that is much better already than 2 to the power of n. That is an amazing improvement in complexity. You can check that you can pick a calculator, a Python console, whatever, and check that you can get to quite larger numbers. So that is great. And we just made one very simple pruning. And as you can see, proving that it actually has a good worst case complexity has not been too hard. We just had to slightly modify the runtime complexity recursion. And this is nice to know this pattern of, when you have these simple recursions justifying a backtracking solution, if you manage to make the recursion go further back somehow, that will have a real and important runtime impact, because theoretically, when you make the recursion, that makes it grow slower by an exponential factor like this. It basically reduces the base of the exponent. That is very, very interesting. But we're not going to stay here. We need to get a better algorithm yet. So what are we going to do? Well, if you paid attention to this idea, it will be clear to you now that we basically want to get rid of vertices of degree 1, 2. Because if we can guarantee that we will always remove one vertex of degree 2, of degree at least 2, I mean, well, we will be able to push this recursion further back and change to n-3. And hopefully that new recursion, which is not Fibonacci, so it's not that well known, will give a lower runtime. And that is the case, it will give a lower runtime. So let's think, what can we do about vertices of degree 1? Well, this is also a well-known technique. When you have in any graph a vertex of degree 1, you can basically assume that it is part of the maximum independent set. It might not be, if you grab any independent set at all, this one might not be part of the independent set. When you have a vertex of degree 1, there exists at least one maximum independent set using it. So you can just use it and you will not lose the optimum solution, which is great because then it behaves exactly as vertices of degree 0. Why is this true? Well, basically it's very simple because of this drawing. If you don't choose any of these two vertices, neither the vertex nor its neighbor, then obviously this is not maximum. You could add the vertex without conflict. So if you don't use this vertex, you must be using its neighbor. But then, because of the drawing, it's easy to see that this vertex only has conflicts with its neighbor. So even though, so if we remove its neighbor and add the vertex to the solution set, it will still be valid, because removing a vertex obviously does not create conflict, and adding a vertex can only create conflict with some of its neighbors, but we have just removed its only neighbor, so this will be valid. And of course, this does not change the size of the independent set. So any independent set without this vertex can be changed into one that does use it. So that justifies changing slightly our if before, and we say, well, if the degree is 0 or 1, two options, 0 or 1, 1 or 0, any of those degrees is basically cool. We have like a greedy method now. In fact, this could be the start of a greedy solution. In any graph, if you have a node of degree 0 of 1, you can just put it in the maximum independent set that you're building. That will be correct, and keep going. And of course, that might solve the problem, because, for example, if you have a cycle which does not have degree 1, but which has one leaf attached like this, well, using our rule, we can assume this is part of the solution, which basically deletes this vertex, and then there are what we get is just a path, so it will be solved by using this rule. So this rule is able to solve trees, any tree, and many almost tree, let's say, almost trees graphs. What I just said might make you think that this is enough for any cacti, for any cactus, but that is not true. This one would not be solved by the rule, because the rule would say, okay, I can use this one, which deletes this one, and then we have a cycle. But basically, by using this rule in a cactus, we can reduce the problem to having many cycles, which are easy, because for any cycle, the solution is just half of the vertices. You choose one and don't choose its neighbor and repeat. Now, then using this new optimization, we can reduce the time further. How much? Well, we will reduce it to, we'll change the recursion, and now it will be like this. F of n will be f of n minus 1 plus f of n minus 3. And how large is that? How does one solve that? Well, I will not prove how these recursions are solved. Those that know how to solve linear recurrences will know how they are solved, and will know why Fibonacci's grow like that. But basically, the mechanical way to solve them is, well, first you express it such that the lowest ones of this is n, just a change of indexes. So you say, you change it to this. Basically, I'm adding 3 to every number. That's it. Now, when you have it like this, you mechanically change every occurrence by a polynomial and take the parameters as the exponents. Then you can simplify. Deleting n. You could have done that directly, but this is like a simple rule to remember. And then you move everything to one side. Okay, great. So we need the roots of this polynomial. And basically that is the trick. The runtime of these functions will be at most the absolute value of the largest root of this polynomial over here, which for Fibonacci is would have been this polynomial. And the number we saw before, phi, was the largest root. This is well known. That is why I am skipping it quickly. But if you don't know it, it's highly non-trivial. Take it as magic, but it has to do with linear algebra and related things. So, okay, here I have a table to help me. And the roots of this polynomial that we have just seen is about 1.46. So that's great. Our algorithm currently with those two very simple checks. Well, it's actually one simple check. If the degree is at most 1, then use the vertex. That's all. That's all that you have to check. Runs in time 1.4656 n. That is much better than the original one. As we ask more conditions, it might get trickier implementatively to avoid paying an extra n in the complexity, because you have to be very careful to keep all the masks and all the counters that you need all the time to be able to make these checks quickly. But I'm pretty sure that all of the checks can be done for basically all of the prunings that we will make. But anyway, at most we will get to this complexity times n, which is quite great actually, because the exponential part has dropped dramatically. Well, is that enough for us? No, that is not enough for us. We will want to basically go one step forward and make sure that when we use the rule, we will use it on a vertex of degree 3 or more. That way, our recursion will always decrease by 4, because when we use the vertex, we kill the vertex, and it's 3 or more neighbors. So that is at least 4 vertices that are destroyed. And that will get us to a better complexity. If we manage to avoid vertices of degree 2, we will reduce to this number, because this is, you can put these polynomials in Wolfram, but basically these are the numbers. What you can see is that they can be calculated, and it gives you an idea of how fast does it grow. It gives you actual correct upper bounds on the runtime. Well, getting rid of vertices of degree 2 is not so easy, because there is not an obvious local rule like before. For example, here the only correct solution would be not to use the vertex, while here the only correct solution would be to use this vertex. So the fact that the vertex has degree 2 is not enough to decide whether to use it or not to use it. But luckily there is a trick, because now we can at least check whether there is any vertex that is not degree 2 or less. We will now want to check that. So in order to know whether we have vertices of degree more than 2. If we do, we pick one of those. So the only complicated case that remains is what happens when every single vertex has degree 2. But that luckily is easy, because the only way for a graph to have all of its vertices of degree 2 is for it to be made of simple cycles. So then we can run a special code for that case. In case that there is no vertex of degree other than 2, we know that the graph is all made of simple cycles, and then the answer is for each cycle, its length divided by 2, rounding down, of course. And basically that's it. We have to check it, but this can be done in linear time in the remaining graph, which is obviously much better than any exponential. If at some point, instead of going with the general recursion, this pruning kicks in and solves the remaining graph in linear time, it is obviously better. So that's not the worst case. The worst case will now be when every single step of the algorithm picks a node of degree 3. And thus that changes our polynomial to this one over here, because this is like the next one, the one that corresponds to reducing by 4 vertices. And that will give us this number. Now, this is amazing and a great reduction, and you can check that this will get you to so the final complexity, just to write it explicitly, will be like this. Possibly, depending on how carefully you manage to do the implementation, you will need one factor of n here. I'm pretty sure that it can be reduced with a very careful bit mask manipulation and counters. Using this algorithm, you can probably go to solve instances for n like 42, and you are guaranteed that it will run very, very, very fast, because we have a theoretical proof that it does. And unless the test case has been constructed to be a especially hard instance, it will probably run faster, because we now have a good intuition that whenever it picks a large degree node, well, it's as if it would be working with a recursion that goes even further to the right. And why am I emphasizing that this is better than square root of 2? Well, as an exercise, you can think of a pretty standard approach to solve this problem using meet in the middle and dynamic programming with bit mask techniques in order to get a complexity of 2 to the power of n divided by 2. This would be part of the divide and conquer optimization times n. Sorry, meet in the middle. So using meet in the middle and divide and dynamic programming techniques, you can get a totally different solution with this complexity. And the solution based on the simple backtracking and adding some very simple prunings by looking at the drawing has gotten us even further. We have reduced the runtime complexity even further, because if you rewrite this, this is the same as saying square root of 2 to the power of n. So the fact that this has a lower base means that it is better asymptotically than this algorithm, and I think it is conceptually much simpler. You do not need to know meet in the middle nor complex or at least nice tricks of dynamic programming. So this is amazing. And if you go on the web and check, you will find some papers by Tarjan, which basically extends these ideas further in a very intelligent way to basically get backtracking solutions with guaranteed exponents, which have an even better complexity. Now, for my second example, I will take another well-known NP-hard problem, which is exact cover. In this problem, we will have m sets, which are all subsets of a universe of n possible elements. So we can basically represent it as bit masks. So we have m bit masks, and each of those represents a set, and these bit masks are of length n. Well, the exact cover problem consists of choosing a subset of those masks such that they cover the whole set of n elements, but exactly. We have to cover it exactly. And we want to use the minimum exact cover. We want to know which is the minimum number of sets from these m possible sets that we have to use to do it. For example, here, well, I doubt that there is an exact cover here. Yeah, there probably isn't. Yeah, there isn't an exact cover. But let's say, for example, if we choose this mask and this mask, we can choose any subset. Well, then basically we will have covered any element that is covered in those masks. So basically, the coverage mask, so to speak, will be the OR of all the masks that we choose. And here it will not be complete because none of these two masks cover this element, so the coverage mask will be not all once, so this is invalid. But still, for example, if we add this one, it will not be an exact cover because even though it covers every element, the OR of all the masks that I chose will give all ones. There are elements that are covered many times. For example, this one is covered twice, and this one is covered 3 times, and we don't allow that. We want to cover each element exactly once, and we want to use as few sets as possible. Well, this is the exact cover problem, which is NP hard, to know if it is possible, and if in case it is, the minimum number of sets that are required. But we can find a backtracking solution to it. I will say that our solution will focus on m and reducing it, but I will assume that n is large and will not concentrate on the value of n. But in case that you know that n is small, for example, if n was equal to 10, then that means that there are very few possible values for the sets. In particular, there are only 2 to the power of 10, which is around 1000 possible sets. And so you can solve it very similar to the subset sum problem. Basically, you can use dynamic programming to say, well, what is the minimum possible number of sets to use to cover this mask exactly using the first I element. And this is very similar to subset sum. So, but instead of adding the numbers, you are using the bitwise OR to combine them, and you have to check that they are disjoint when you do. But of course, that solution has 2 to the power of n of complexity, so for large n, say n 100, there is no chance. We will never be able to use that solution. We have to think of something. This solution will be exponential in m, but will not really care too much about the value of n. It will be linear in n. In fact, since we will be using bit sets, it will probably be something like this. So for moderately small values of n, it can be taken as constant. So then, enough talking. What is the solution? How can we solve it? Well, we can use the fact that this is an exact cover to speed up the solution, because in a similar way as before, we can imagine that the process of building the solution is made of, going set by set, row by row here, and choosing whether to use it or not to use it. And without any proof that we are pruning or anything, that will lead to 2 to the power of n complexity. And we want to do better. And the trick is that we are after an exact cover, and we can use that to our advantage. How can we do so? Well, basically, we know that since it's an exact cover, we can choose one of the columns, for example, this one, why not? And we know that exactly one of those sets that are that have a 1 in that column must be used. So the solution either uses this, or this set, or this set, but exactly one of those 3 will be used. So we can take that as our basic step for the recursion. Similar to the previous example, if we pick one of them, for example, we try to use the first set, then we say, okay, this one goes in the solution, and that means that all of the columns having a 1 there are already covered, and we will not be able to use them anymore. So we would have to delete it and ignore them and make as if they don't exist anymore. That can easily be done using bitmask, because that is like making an AND to all the masks. Instead of doing an AND to all the other masks, we can keep a mask of live bits, and whenever we check a mask, we actually first AND it with the live bits mask. But that's basically it. So at any time, you pick a column that is still alive, still has to be covered. You checked which of the sets cover that bit, and you try all those possibilities. It must be said that in the previous case, when we choose this one, we must already remove from consideration, so we will need a mask of valid sets to use, which starts with all the sets on, but will be removing sets from the allowed sets as we progress. Well, whenever we choose one of these sets, when we were looking, for example, for the first column, we immediately remove all of the others. In fact, we should remove not only those that clash with it on the first column, which is the one we were looking for, but we should remove any set that clash with our current element at any column. for example, this one clashes with our element in this column, and thus we cannot use it anymore. And this one clashes in the last one, and thus we cannot use it anymore. So in this case, this solution will fail, of course, but we have to destroy them all. And again, we can do that efficiently if for each if we pre-compute before running the backtracking for each set a mask containing all of the other sets that must be destroyed whenever this one is used, because then we can use that mask to very quickly destroy them all. So this is a great example of using bitmask and pre-computation, both. And those we go on trying until we manage to cover everything. If we manage to cover everything, well, we update the best solution that we've seen, and if we don't, we should stop. We should say that we can make this backtracking solution even better and perform even faster and much faster in practice by using the branch and bound technique. Basically, this is a very common way of pruning that can be used on almost any backtracking problem which involves optimization. This one is an optimization problem. We want to cover with the minimum possible number of sets. But I will explain it later because it is a very, very general technique. But even if we don't do it, we still can give a great complexity guarantee. Why? Well, let's think about the process of this solution. It starts with the original set, which has all the m possible sets to use. And then it selects a certain column and it checks which ones have a 1 on that column, and the branching factor, the number of children in our backtracking process of creating new sub-problems to solve, will be equal to the number of elements that have that 1. We don't know how many. Here in this example it is 3, the branching factor, but it will be exactly how many ones we find in that column. Among, of course, the ones that are still alive. And what about the size of these problems that remain? Well, we are not sure of the exact size because, as before, maybe we pick this one and this destroys everything. We saw an example. But we know that at the very least, all of these ones must be destroyed too, because they share at least this bit. So without looking at the full matrix at all for our analysis, we know that if the branching factor is 3, like in this example, then at least the problem size in terms of how many sets we have is reduced by that much. So these problems will be size 3. And the same holds at any node in the chain. If we branch into 5, then in the column that we chose to look at that time, there were 5 ones. And those, at the very least, those 5 sets are destroyed. And so the new problem is reducing 5. So if this was the total minus 3, this one must be the total minus 8 or less, and so on. Well, whenever we have this property, let's think what the worst case can be. What is the worst case? Well, this is interesting. Basically, if we assume that the branching factor for any level is constant, which makes sense because let's assume that the branching factor can be chosen by an evil enemy that wants the tree to be as large as possible, so that we get to the worst case. Well, for the first step, whatever you choose, say you choose k. Okay, all the problems now have size m minus k. So each of these one, for this abstract analysis that assumes the worst and assumes that at most that we will have actually m minus k size in all of them, they are all the same. So whatever is optimal to produce the worst possible tree here will also produce the worst possible tree here, and so we can assume that the branching will always be the same. With that in mind, basically what we can check is that we start from m, so let's say m is 50. I don't know, just because there are 50 sets. Well, okay, we are counting how many nodes we are creating. Well, if we branch into k, the number of nodes gets multiplied by k, but the number of sets remaining is reduced by k. So, for example, if we said we start with one node, we choose to branch into 5. Okay, now we have 5 nodes, and we have M45 remaining size. Okay, we now choose to branch into 10. So we get to 5 times 10, which is 50 nodes, and we will get 35 remaining, and so on. So the question that we're asking is basically this one, which is something nice to know apart from backtracking. This might appear on itself. We can multiply a series of numbers, whichever numbers we choose, and we want to make the product as large as possible, because remember, we are trying to make our tree as large as possible to know how worse it can be, how bad it can be. But the sum of all our numbers, which is how many sets we've been consuming, can be at most m. So with a sum of at most m, how large can you make the product of numbers? You don't have any restriction of which numbers or how many numbers you can make. You can choose any number, and you can just put any numbers on your product. They are integers. That's important. Well, this is an interesting problem, and the solution basically is that you always want to choose 3. This is the asymptotical result. If your number m is not a multiple of 3, then you will have to adjust a little, but asymptotically it will be the same. So for our purposes, if we miss by a constant, it's fine. We can basically assume that the branching factor is always 3, because that is the worst case. The reason why 3 is the best is that basically you can analyze this problem without the integer restriction, and then basically you can check that you want to maximize the product of all the numbers, but that is the same as maximizing the logarithm of the product, and the logarithm of the product is the sum of the logarithms of the numbers. And now, since this is the sum, it is a much easier and well-known problem, because you want the sum of the original numbers to be m, so and you want the sum of their logarithms to be as large as possible. So it is as if you have a budget of numbers, and each number has a budget, how much it costs, and a value, how much it adds to the sum that you're actually interested in. So basically, this is like the knapsack problem, but in the continuous case. And for the continuous, at least for the asymptotically optimal solution, you would like to solve the continuous case. So how good is a number is basically a function of log of x for the number x divided by x. And when you analyze this function as a continuous function, its optimum is achieved at e. So e is the ideal number. You would ideally like to multiply e times e times e times e times e times e, like that. If your number is not exactly a multiple of e, the same. You will have to adjust a bit, but this is like asymptotically, this is the solution. Back to our problem where we have integers. What does it mean for our solution? Well, if you know this property of that 3 is the best for integers and all that, then you don't have to discover it in the moment. It is well known, and you see, oh, okay, so the worst case is 3, and thus we will have always branch factor 3, and so we will have m divided by 3 depth, because the size is reduced by 3 in each step. So this is the number of steps you can make. And at each step, the number of nodes is multiplying by 3. So 3 to the power of m divided by 3 will be the final runtime complexity. And this is approximately 1.442 to the power of m. So this is much better than 2 to the power of m. And thus, using this this technique of choosing to do backtracking like this, you can actually prove that you have a fairly good complexity. This algorithm will probably tackle without too much trouble instances as large as mn up to 50. This should run reasonably fast. Now, as an example of a problem of the second kind of good problem that I mentioned before, I would like to show you an example that is from the last Latin American ICPC regional, and it was problem A, if I remember correctly. In that problem, you had a square sheet of paper of side, with sides of length 1, and you basically wanted to create marks at a certain height. Initially, the only mark that you know is basically the corners at height 1, h equals 1. But the allowed operation is like this. You pick basically two heights that you want, that you already know. Initially, we only know one, so we will have to pick 1 and 1. It can be the same height at both sides, no matter. And draw a line from that point to the opposite point in the base. So either 0, 0 or 1, 0. For example, the first step is always like this. There is no other option. And this produces height 1/2. This is 1/2. And now we have basically two options, 3 options in fact. Well, one option is to do the same again, which makes no sense because we already have that point. So we have two new options. We can choose 1 on one side and 1/2 on the other, or we can choose 1/2 in both sides. And the operation is the same idea. If you choose 1/2 on one side and 1 on this side, for example, then this one is joined to the opposite base corner, let's say, corner at the bottom. And this one is joined to the opposite corner, which is already drawn like this. So this is the point where they meet, and this will be the new height that we produce. While if I choose 1/2 and 1/2, then this is the one I would trace, and this is the new height that I would produce. So the input in this problem gave us a fraction as two integers. For example, if the input was 4, 5, it means the fraction 4/5, and if the input says 2/5, it's that fraction. If it says 1/10, it's 1/10, etc. And the question is, what is the minimum number of steps that we must make in order to produce that height, or say that it is impossible when it is impossible. So the first part of the problem is to understand what things, how can we produce? I mean, how does it work? How does the operation work? And we can translate it to a much nicer form. So let's first of all calculate what the operation does. Say we have height A on this side, and we have height B on this side. This is obviously symmetric because you could flip the drawing and the height would be the same. So combining A with B, what height does it produce? Okay, we can write the equation for this line containing A. That one starts at 0, so it is A minus the slope of the slope of this. The slope goes A in 1 unit, so it's simply minus A x. So this is the equation for this line, and the equation for this other line is very simple because it goes through the origin, and it goes a height of B in 1 unit, so it's simply B times x. And we want this to coincide because we want to find the intersection point, y equals any of this. So let's solve for x, and well, the solution is simply x equals a divided a plus b. So we're interested in y, actually, not the x point. We're interested in the y point of the situation. So we can replace here, for example. Replacing here would give the same result, and we get that this is the new point. So this is the combined operation. Not so bad. It's quite nice. If we have height A on this side and B on this side, in a single operation we can produce height AB divided by A plus B. And by trying various examples, for example, you can, well, starting with 1 and 1, we see that we get the product divided by the sum, so it is 1/2. And then we can check what happens if we combine, for example, 1/2 with 1/2. Well, in general, if you combine A with A, you will get A squared divided by 2A, which equals A divided by 2. So that is nice. 1/2 combined with itself is 1/4. 1/4 combined with itself is 1/8. So basically the denominator doubles, which is nice. So what for different numbers? For example, if I combine 1 with 1/2, what do I get? Well, we would get the product, which is 1/2, divided by the sum, which is 2/2 plus 1/2, just to make it easy. Okay, and that is, well, I can cancel these 2 with these 2, and I get 1/3. So you might get the pattern already. After making a few examples, we see that the numerator is always 1. We don't seem to be able to get fractions having numerator other than 1. And the denominator is simply the sum. That is, combining 1/2 with 1/1, which is this number, seems to sum the denominators. And the same with 1/4 with 1/4 gets 8. Well, this rule is actually true. It's easy to see when you notice that this one is the same as, if we divide both sides by AB, you get 1/B plus 1/A. So if the original height A was actually written as 1/A prime and B was 1/B prime, then again this says that the new height is 1/, but this is actually B prime and this is A prime, so it's the sum. So if we write that Y is actually written as 1/Y prime, the rule is simply that Y prime is the sum of the A primes. And basically this proves that the rule works. All your fractions can be written as 1/something, and that something is the sum of the original primes. So since we start with 1, 1, we will always get integers. And that means that immediately, if the input gives us a numerator other than 1, the solution is impossible. But all other cases are obviously possible, because we can just keep adding ones and we will get to any number. And the question now is, how fast can we get? That is, how many operations do we need? And well, this is a well-known problem. You can look it up in Wikipedia, and no polynomial solution is known for this problem. The problem is framed as the optimum exponentiation by products, because if you want to compute, let's say, a to the power of 10, you can compute a to the power of 5 somehow, and now you can square it, for example, and get a to the power of 10. So in one extra product, because you do a to the power of 5 times a to the power of 5, with one extra product, apart from whatever you need to compute a to the power of 5, you can get to a to the power of 10. So the problem is to compute for a given exponent what is the minimum number of products that we have to do. And this is there is no polynomial algorithm known for the computing the optimum number, the ideal number. But we have bounds, because, for example, we know how to do efficient exponentiation, because we know the repeated squaring or binary lifting method, which is basically like this. You go to half the number and now you square it. And for example, to get 5 here, since it is odd, I will make a times a to the power of 4, and that I want to get squared. And this one is even, so I will square it. Like this, square. Okay, so this is the sequence that the repeated squaring method uses to get a to the power of 10. And this uses 1, 2, because it has to square, 3, 4. So the method of repeating squaring, which we know uses at most a logarithmic number, it uses at most 2 times the logarithm, I think, multiplications. In this case, uses 5. 5, am I right? No, 4. Only 4. Is that optimal? Yeah, I think it is. But notice that there are different ways to get there. This one, I started from having only a. I created a squared. Then I created a to the power of 4. Then combining these two, I can create a to the power of 5. And squaring this one, I can get a to the power of 10. So 4 multiplications were used because each multiplication creates a new number that I don't have access to before. But another method could be, okay, start with a, just square it again, and now just combine these two. This is very similar to the other one. And we will get in the same number of 10 steps to the target. But we create different intermediate powers in the process. So that might make you see that the problem might get harder for higher numbers. But the thing is that the method of repeated squaring is not always optimal. Sometimes you can get better results doing something different, something else. Why does this matter? Well, because this is clearly the same as our problem. It is framed as a geometric thing, but we've found that the operation can be rewritten as, okay, you start with only the number 1, and you can create a new number in a step by adding 2 numbers that you have. It can be the same, so you can actually double a certain number, and you want to get to the target number as fast as possible. And that is exactly what happens with the exponents. In this setting of I want to make an algorithm that makes as few multiplications as possible and gets to the target power. So what's the trick? Well, given the bounds in these problems, the numerator is at most 100 and so is the denominator. But we already know that if the numerator is not 1, then it is impossible. So actually the only input to this problem is the denominator. So we need to know what are the numbers of optimal powers, the optimal number of products to create each number from 1 to 100. And those are very few numbers. So actually it doesn't matter if it takes a while, maybe like 5 minutes on your computer to end. If you have the right numbers, you can hard code them in an array in the code and submit it because the input is very, very small. So this is clearly a problem of the second kind of good backtracking. The input, the possible outputs and inputs are, once you realize these nice observations, it's very small, just 100 numbers. And so you just have to calculate this number from 1 to 100. If you're able to do it in reasonable time, then okay, you hard code it and that's it. And I think that an efficient program can probably even pass for this one. An efficient backtracking should probably pass even without needing to hard code. Although once we get to this situation, it's the same. It's totally possible to hard code because it's so few numbers, so not too many. So yeah, now the problem is to make a reasonable backtracking method. And since we know the inputs, we have to run up to 100. We can test it on our machines. So we will know when we submit whether it's fast enough or not. If it doesn't end on our machine, well it obviously will give time limit. And if it ends completely for the 100 inputs in our machine, then we can basically hard code them and eliminate the time factor here. So how do we make a good backtracking for this? Well, basically, the state has to be which numbers do you have. My suggestion for this problem, because maybe you'd say, okay, the state is the set of numbers I currently have, and the operation to move to a different state is to pick two, consider they are sum, and add it to the set. Well, that is correct, but remember that our sets will go to 100. So if you just do like BFS on that set. Now, at first, for this problem, I thought that BFS would not be fast enough because there are too many sets to consider. But that turned out not to be the case. I tried it, I implemented it just to check, and I managed to get a very fast BFS solution that computes this function for all numbers up to 100 super fast. But I had to optimize it quite a lot. My first attempt almost crashed the whole memory of my 16 gigabyte computer because well, it generated too many sets unnecessarily and in a too inefficient way. So the final implementation is very optimized and uses in fact that the graph is DAG because you increase the size of the set each time. So that's important. That allows you to go in by steps and know that you will not ever see the same set from a previous iteration again, so you can completely forget it, and that reduces the memory consumption and so on. I also used bit sets. I used well, not bit sets, but two longs used as a bit set of 100 bits. So yeah, it ends up feeling similar to a backtracking about the same optimization skills are used for both. So this one can be solved by BFS, but it has to be quite optimized, not the standard BFS. And of course, the final implementation only uses vectors, no set or anything. So yeah, it's tricky, but I will share the code with you because it's interesting. But anyway, that surprised me, but I think this problem is much better suited for a backtracking because it's probably easier to understand, and I think it will be good enough because in the end it will end up iterating just like BFS, but probably less because it's easier to add pruning to the backtracking. And this problem has the nice property that it's quite easy to achieve lower bounds because it's easy to produce valid but although not optimal solutions, but they will very often be optimal. One is the fake dynamic programming, because basically you can imagine that, oh, okay, to create number x, I can try all numbers a, b, such that a plus b equal x, and take the minimum possible value across all ab of the number of operations I need to create a plus the number of operations I need to create b. And well, this is false basically because it doesn't take into account that many numbers will be repeated in A and in B. So this double counts a lot, but it is a bound. This bound can be improved a lot in a not so hard way by instead of just adding the numbers, creating the solution sets that the dynamic programming algorithm would achieve, and then simply merging them. And then computing the size, the pop count of the union. So that will eliminate duplicate. It still will not be optimal, but in many cases it will. Because, okay, it will take the merge of both as a solution, and that will be valid a lot of times. For example, the number 2 has to be produced basically every time. You have to start 1 plus 1 equals 2. So that will automatically be taken care here. So that's a pretty good one. And also we have the repeated squaring solution and very similar ones, repeated squaring or binary lifting. You can just use the normal algorithm to make powers and count how many that takes, and you know that the optimal answer will be at most that one. Oh, sorry, I said lower bounds, but these are upper bounds. Anyway, this one depends on whether you're minimizing or maximizing a solution. But if this was a maximization problem instead of minimization, well, this would be like lower bounds. Like, you know, you can do at least this good. Maybe better, but at least this good. But since this one is minimization, this is an upper bound. But anyway, it's easy to give at least good solutions, and that helps a lot for pruning. We will see that with branch and bound. So due to this property that it's easy to create efficient and simple, but yet very good, I mean very close to the optimal solution. You can add many more, and it's easy to, if you add a few rules, you will get almost always within 1 or 2 from the optimal, not very far. In fact, experimentally, if you go to 100, the maximum number of operations is 9. So you are never too far from that, from the optimal. And that helps pruning tremendously. So this problem will be very attackable using branch and bound, which will be the final thing that I'll mention. But just to give you a glimpse of how you could code it using backtracking, well, I would like to use the principle that I want to generate the solutions, and the solutions here are the sets of numbers that I can produce. And I want to generate them only once, not in multiple times, which is something that my BFS solution has that problem. It generates numbers many times. The set, it arrives at the same node from many different paths, so we have to check for repeated. And we can avoid it if we have the set, and imagine that we are going to create it from small to large numbers. So that is an extra restriction that we have. We're going to always create a number larger than the last one that we did. So from the set 1, we can move to the set 1, 2, from there to 1, 4. And now adding 1 and 2 will not be allowed, because that would produce 3. If you wanted to do that, you had to go through a different path. You had to do 1 plus 2 now, and only then create the number 4. That way, the possible paths make up sort of a tree, let's say, starting at 1, and each path corresponds exactly to one possible set of values that you can produce, because now we have the restriction that each number must be larger than the previous one, and must be created by summing 2 of the previous numbers. So here, for the first time, we have 2 options. We can go to 3 or to 4 and skip 3 completely. From here, for example, we can go to 4, 3 plus 1. We can go to 5, yes we can. We can go to 6, yes we can. And that's basically it. So this node would encode, okay, I arrived at the set 1, 2, 3, 6, and so on. So this is a quite efficient way, and each set is created exactly once. So you know that you won't be repeating, so you don't have to check for repeated. That is very, very convenient. That reduces memory consumption a lot. And in these algorithms, using less memory almost always translates into using less time, because more stuff fits into the cache memory. So yeah, you can do that. And even more, when you check which number you can generate next, you could do something quadratic by checking all these numbers a lot, but you can get it down to linear time, because instead of checking all pairs each time, when you add a new one, you can do this by modifying a global array of possibilities. And in that global array of possibilities, you will be counting in how many ways you can form with the current set each number. So for example, it has indexes 10, 11, 12, whatever. So currently number 11 can't be formed, and number 12 can be formed in one way, say. So if you add a 5, for example, to your solution, and your solution is currently, well, or let's say you add a 7, I don't know. And this is your current solution. Yeah, this is invalid. Then you added 7, so now you have to update the global array of how many ways, I mean how many pairs there are that sum up to this number. Well, the only pairs that get created are those with the number 7, which is the new one, and each of these numbers, including the new number 7. So basically you would have to add 1 to 7 plus 1, which is 8, so 8 gets plus 1. 7 plus 2, which is 9 plus 1. 7 plus 3, which is 10, so plus 1. 7 plus 5, which is 12, so plus 1. This one will now be two ways to create it. And 7 plus 7, 14. And the good thing about it is that updating is just linear time, and also that undoing this operation is very simple. You go through the values again, but now you subtract 1. That is the reason why I use counters instead of just Boolean values. That way I can easily undo when I remove it. So this is very efficient, just linear time, which is actually like 9 when I say linear instead of 81, so 10 times faster. Because these things are quite short actually. These paths are at most 9 in practice. At least when you go up to 100. You could go to higher numbers with this. Well, when you are checking what numbers you can possibly use for the next one, you would like to know which numbers are have a positive value here. And well, you can actually do that by iterating this set and checking which numbers are positive. But we can do even better. I hadn't thought about it before, but we can even delete all of this and just have masks, because masks will be very compact, so it is quite cheap to actually copy a mask. For example, for this problem, the numbers go up to 100, so just 2 long longs are enough to hold a mask of 100 numbers. Since all of this is exponential, in general, a very little number of masks will hold a very large number of useful numbers for this purpose, and this means that actually when you add a 7, you can you can put ones into the mask for each number that must be added to 7. And in fact, I think you can get it down to constant time, because if you have the mask for these numbers, then the mask for these numbers plus 7 is just that mask shifted 7 places. So that means that you can, with using tricks with bits, you can actually get the new mask for all the new possible elements by a simple shift. So that should be super fast, constant time, assuming that the number of masks we have is, we can call it constant. So yeah, that version with mask would be actually even faster. So this should be very, very fast, and it wouldn't surprise me that it actually manages to go to numbers quite above 100. So this should do much better than the BFS algorithm. So yeah, this backtracking scheme together with the branch and bound method should do super well for this problem. So yeah, you can try it, and the good thing is that it goes to 100, so you can try and start from the most basic method like this with almost no pruning, and you can start optimizing and see how far you have to go until you can run it on your machine, because once it runs, again you can hard code the 100 numbers. In the end, in this case, I got a solution that runs so fast that I don't need to hard code, but maybe the very first version of the BFS, for example, ran in like 2 minutes and used 8 gigabytes of memory. That I cannot submit that, but I can hard code the 100 values. So yeah, that is enough for this problem. So and before I forget, I would like to mention a few very useful, I don't know how to call it. Let's say, okay, yeah, I think I know. Let's call it topological pruning. These turn out to be very effective prunings for problems, especially involving a grid, especially involving paths on a grid, simple paths on a grid. So you have a grid where you have to walk, and you cannot cross yourself during the path. This is the most common case. And here you can add a few prunings that might seem simple, but actually prune a lot. They are very, very effective, and they are based on this idea, like if you have a closed curve and something is inside and you want to go outside, and you will have to cross. Well, that's it. That's the idea. For example, let's suppose that you have a problem where, for example, it is a Hamiltonian. There are obstacles, maybe, I don't know, but it is essentially a Hamiltonian path like problem. So you have to build a simple path going from the start to end and crossing and going through all the valid nodes. Then, if you concentrate on one node, if you go in through this way, fine. But what happens if you go out like this? Well, if there are no obstacles, you will eventually have to go here, have to go here. And it's sort of symmetric. So let's imagine you go up first. Well, looking at the drawing, it will sort of close the path. So if you do something like this, this region and this region are completely separated. So if you want to go to this one yet, you will never be able to come back here. So the only way that this can be solved is that actually this is all already solved. Now, checking that is typically expensive. So instead of that, it is typically better to just make a very simple local pruning. The thing is that this one over here should already be solved. So really, essentially, the critical part in this pruning is that I'm here, this one is blocked because either because I was there or because it's an obstacle, whatever, that I have been here before. That way I know that since I was there and now I'm here, I can close the cycle. This one must be available and this one is available. Then with this pattern, for example, if I find this situation of these 4 squares then that I described, then if any of these ones in light blue is free right now, just like this one, for example, if this one is free or if this one is free, if any of these ones is free, then there is simply no way to solve this. Because again, for example, let's say you're concentrating on this one. Well, you can actually see all of this border of these interesting squares like a closed region, and if you go through the border of this region, you have free on opposite sides, and I've been there in the middle. So any cycle that closes this will have to separate these two free ones. So this is quite similar to the planarity class. If you've been to the lecture on planarity, this will feel correct. And this is a very fast to check condition, and you can make many other variations of this based on the same idea that if you close a loop, you have to go through. For example, one specific but very useful example concerns the borders of the grid. Imagine that it doesn't even have to be Hamiltonian now. You might leave cells without visiting, but you want to trace a path from corner to corner on a rectangular grid. Well, if any time somehow you manage to get to the right, that is to one of these squares on the right area, then it's easy to see in the drawing that you have cut the region in half and your target is down. So right now if you go up, you will lose. So you can add a special pruning related to the border, that if you get to a border cell on the right, then you have to go down. If you can't go down, you've lost. And if you can't go down, you cannot go up. A very similar condition holds from the bottom. You have to go right if you get to the bottom. And for these two edges, you can get some interesting conditions still, because you know that you traced a path there somehow, and then if the cell on your left is still free, then you cannot go there. That's basically it. You cannot go left now. It might have been the case that you came from the left. That might be possible. You did, okay, this is the path, and here, that's fine. But if you're here and the left option is available, so you haven't been through the left, you've entered here either through the right, which is very similar to this. It would be something like this, or from the top. Then you can actually check, basically in any case, you can't go to the left, because if you do, we'll have done this, and you're trapped. So basically you can add the rule that on this top part, you cannot go to the left. Any edge that does something like this on the path means that you've lost, because any path to here that doesn't come from here has to enclose this edge, and there will be no way to go back, no matter how hard you try to avoid it. So on the top you can put the rule never go left. On the left you can put the rule never go up. So this is a very interesting but very common condition on problems having this grid structure. And in order to finish, I want to talk about the branch and bound method, which is a method of optimizing backtracking and creating some prunings in order to reduce how much you have to search. This is not used that much in like official problem solutions. At least this is not so common now. But this is a very powerful and effective technique in practice because it really reduces a lot how much you have to explore. It reduces the runtime of backtrackings by a lot. This is quite empirical. So if you are going for a backtracking, like, oh, okay, I want it to be fast, you have to consider this, especially the upper bound check. That one is the most important, very powerful check, and it's most often just adding a very simple if in the main backtracking function. So you probably want to take it into account. The check is basically, if I cannot do better than the best global solution that I have ever seen, that's it. That's a very effective pruning. But what is the branch and bound method in general, in its full generality, just so that you know it and it might be useful in other contexts? Well, to recap, we see the backtracking process as a tree starting from the root, and from there we branch and create new subproblems to explore. Let me emphasize that this will be used mainly to find solutions for, let's say, maximizing problems, for example. So let's concentrate on that idea. We want to find the solution that we can create at the end of this process that has the maximum value, and we somehow calculate the value of solutions. Well, the branch and bound method will work by having a global variable, and this one is critical. This is the most important part of the method. Let's call it best, which has the best solution, or the value of the best solution. What do I mean by the best solution? The best solution that I know that exists, basically. This is a global variable because no matter on which branch you are, if at any point in the algorithm you see a solution that is better than the one you've seen before, you update this global variable. It cuts across the whole recursion, across everything. It's a global, an ugly global. That's it. And this is the most important part. If you've used something like this and then you put a condition using this variable to prune, then you probably already done a branch and bound without knowing it. This is the super effective check. Checking against the best solution that you've ever seen is very effective in my experience. It reduces a lot, much more than other things that you might think will not help too much, at least in optimization problems. Well, this is the key ingredient, a best variable that we will update all the time with the best that we've seen. And then for each node, we will compute two values. It's low and it's up bound. That's the key to bound. The method of is branch because, like backtracking, we branch into different possibilities. But then we want to bound those possibilities. And the full method will use two bounds, a lower bound and an upper bound. But the most useful is generally the upper bound. In this case, where I am always talking about a maximization problem. Of course, this would be the other way if this one was a minimization problem. So basically, the upper bound is the optimistic one. This one is optimistic. The idea is that we must somehow compute a bound for each node. In particular, the bound for the root will be a global bound for the whole problem, which means that for that whole subtree, any solution that we find will be at most upper. Yes, that is why it is optimistic, because I am maximizing. So this is a value. The idea is that these values L and U should be efficient. For example, the optimistic one, if we are in a problem where we want the shortest path or something like that, and there are obstacles in a complicated grid, I might just use the Manhattan distance. So if I know that I am currently here and I want to get here, well, there are obstacles and I would have to check the grid and I don't know what, but at the very least I have to move 1, 2, 3, 4, 5, 6 times. Just subtract and get the Manhattan distance. So upper is 6. That's it. This is the idea. Ideally, you would estimate as good as possible, but if it is too expensive to compute a good bound, you can just go on and do the recursion, and it will be better. The idea is to quickly have a bound. If the bound is very good, you will help prune. Because what is the idea? The idea is that at each node, you will add a check. And the check, I already said it. It is, if I cannot beat the best solution that I've ever seen, break. So the check is like if the upper for the current node, which is the best I will ever be able to get, is lower than best, and remember, best is a global variable that I keep all the time. If this happens, break. Because even if I'm optimistic and I, oh, well, again, this problem that I used as an example is a minimization problem. So actually, the optimistic bound is the lower one, so this one would be L. But the idea is the same. If I am maximizing, for example, I have to maximize the remaining time. Well, if I start with 10 seconds on the clock, well, and each step is 1 second, since the minimum distance is 6, I will at most get 4 seconds on the clock. It's the same idea. But anyway, this is the check for a maximizing problem. The idea is always the same. If even being optimistic from this node, anything that doing more steps, I will never beat the best that I've seen, cut. That is the critical idea. And it sounds very simple, but it in my experience, it's one of the most impactful checks that you can do. When you add this line, the backtracking runs incredibly more quickly. So I would recommend that you try to use it always in any backtracking that you do. Even if your upper bound is very silly, well, it doesn't matter. You will have a best, and if your upper bound cannot beat the best, just stop. For example, a typical simple upper bound is when you have a cost that you are computing, how much you've walked. The cost that you have already paid is typically a bound. You will not get less cost than that. Oh, again, I keep talking about minimizing problems instead of maximizing. But for example, I don't know, imagine you want the maximum independent set problem. Well, then you can simply bound it by all the nodes. If you are very lucky, you can grab all the nodes remaining in the graph. If you are unlucky, you can't. But at most, you will get all the nodes remaining in the graph. So that will be an upper bound. And a detail that I have to mention is that this bound is for each node. So each node will have to, when calculating its bounds, consider that there are decisions that have already been made. So basically, these bounds are refined as we progress. The upper bound for a child would have to be at most the upper bound of his parent, because it's still valid. Whatever we did for the parent, it is still a valid bound now that we have already fixed the first decision in the past. So if the function you use to compute the bounds does not have that property automatically, well, you might consider taking the minimum of the previous bound and the current bound when you go down. And this might be relevant because the best keeps increasing as you progress. You find better and better solutions. So this same bound might help you prune later. I mean, this bound in the parent might be helpful for pruning in the child if later, when processing the child, we have somehow found a better best. So for the example of the maximum independent set, maybe the first step here was to already select one node for the solution. So here we might have one vertex already selected as part of the maximum independent set. So here, when I said the upper bound is all the remaining nodes, well, actually the upper bound here will be 1 plus remaining nodes, where 1 is the size of the set that I have already constructed. And the same at every node. Actually, the bound would be, well, the best that I can get at all is whatever I have already put into the maximum independent set in this stage of searching, plus all the remaining nodes, because I'm optimistic and I assume without looking that it's independent. It might be all independent, I might be lucky. I haven't checked yet, but without looking, that is the best. And maybe when you check what you have already put in place, even adding all of the vertex, which is optimistic, that might still not beat the best. And that's the idea. That will help you prune more. But you cannot do this pruning if you don't have this optimistic number. So we have mentioned U, we have mentioned best, but we still haven't said when do we updated it. But we haven't said anything about L. Well, L is not always used. It's much more common to use L. The idea would be to get a lower bound in a maximizing problem, which is typically a greedy solution or a simple solution or a direct solution that can be computed quickly. For example, the problem that we saw before actually had greedy solutions quite easily. In that case, it was a minimizing problem, so L would be U, but it's the same idea. The roles are reversed. So in that problem, it was easy to say, okay, from this position, I can at least make something that is that has value 10. So you can give, this is used to give one solution. So of course, the nodes where you always have L, even without changing anything and thinking, are the leaf nodes. At the leaf nodes, you have completely constructed the solution, so you can actually evaluate it. And actually in the leaf nodes, you will have a concrete value, which is the value of that node. There you won't have two estimations, or you can think that both values L and U will coincide. So this is one place where you definitely have a value for L, for the lower bound. Whenever you have a value for the lower bound, be it in the leaf nodes or up the tree, doesn't matter. Anytime that happens, you check against best, the global variable, and you update. And if it is better, you update best. So that is the idea. The values L, these values, help to quickly, even before constructing a full solution and exploring a whole path. If a path, let's say a subtree, is very good because you made a first decision that is excellent, and that guarantees that no matter what you do next in the next 50 steps, because you took such a good first step, any solution that comes out of this subtree will have a great value at least. So it will have an LU, but L is very good. Then here you compute this bound L, and you will know, oh, this immediately beats current best, so you update it. And that's why they are useful. Computing a lower bound helps you quickly update best, and of course updating best faster helps you prune more. So that's why they are useful. But it is very common that you don't actually have a value here in the intermediate nodes. You only evaluate final solutions, and that is fine. That is okay. In that case, it's the same as if all the L values were minus infinite. So you assume, oh, well, solutions that come from this subtree could be very bad. I have no idea. And then when you get to the leaf node, you will find, oh, okay, I could make a value of L. Also, note not using branch and bound at all is like always using the values minus infinity and plus infinity. So in this check, you are super optimistic. You say, well, I don't know, maybe there is a solution incredibly good in this subtree, so I have to check it. I cannot prune. So this if is the same as nothing. And basically you only have definite values in the leaves where you will never be branching anyway. So that corresponds to not using the branch and bound method, which in fact I think we never used this method explicitly before in the examples we saw. So sometimes it is not necessary. Basically, if you reduce the branching factor, maybe that's enough by itself. But this is a very powerful pruning that is based on the actual values over which you are minimizing or maximizing. These are not based on whether the solution is valid or not, which I think most of our examples focused on that, whether the solution was valid or not. This looks at the values and concludes, oh, okay, this subtree might get a lot of valid solutions, but given my bounds, I can be completely sure that they will never beat the best one. So I will not continue searching. And so that's it, basically. When I look at it like this, you might imagine that there are many different orders that you can, many strategies of in which order to branch. Because maybe a common strategy is to actually have a priority queue and always branch with at the value having the largest L or the largest U, or maybe the largest average between the two. I don't know. But you can use them to make an informed decision about promising paths. Because basically, if a path has a large value of U or a large value of L or both, well, it is a better candidate to get good solutions, even if you can't prune yet. So say, for example, that you have a node of 110 and a node 211. So here best might be actually 2, because the best that you know that the solution can be is 2 because of this L value. Best is always the best L value that you have ever seen. Well, you still cannot prune anything because both sets might contain the optimal solution, but just looking at these values, it is quite intuitive to go for this one first because it looks like it might be more promising. But I've actually never used it in a problem, so you don't have to use it. By far, the most common thing to do is just the normal recursive DFS and go in the normal order. And actually, if you are not computing L values in the middle, or your bound for L is quite bad, it is recommended to use DFS, because actually DFS will make you quickly get to the bottom and quickly get to have actual useful bounds, and so that will help the pruning. So basically, I would say that you always do DFS unless you're very sure that you might have very good L bounds, and then it might make sense to do something different. Well, and that's it basically. One detail about the implementation: these values L and U are typically not stored at all. They are not like variables that you have to keep. They are typically just calculations that you do on the spot when you decide that you will explore a node. So at that time, you, for example, first calculate L, which is a pessimistic value, like, okay, no matter how bad I do, anything from this subtree will have value at least L. And you use it to update best if necessary. If that pessimistic value already beats best, then you update it. If it doesn't, okay, it keeps the same. And after that, you check your value of U, because that's the optimistic value. If the optimistic value cannot beat best, then you stop. You completely ignore the subtree and return to the parent, because you can be sure that you will not win. If none of those occur, then you just branch normally and let the children do the same for the L and U values. So this is basically all that I have about backtracking. I hope that you found it useful, and good luck on the contest. Bye!